Think back to your first days at university in your EE class. Your professor probably drew a picture something like this. And this is the ideal transistor, controlled either by voltage or current. And he explained to you how circuits would work with a transistor, with a switch that's controlled by other electronics. Now, we've been in the real world for a long time at this point, and we know that this is not a really very good model of a transistor. Transistors suffer from series impedance, known as RDS(on), and they suffer from parallel capacitance, known as COSS. And most power supply designs, topologies, architectures, almost everything you come across in power engineering is going to be concerned with and limited by these two parameters. The losses caused by these components are, for the COSS, it's half CV squared, and because it's a capacitance, it discharges through the RDS(on) when the switch is turned on. And so there's a frequency component. So half CV squared F are the losses associated with the capacitance. RDS(on) is only active when the switch is conducting, and the losses here are I squared R. We get closer to the ideal transistor if we can minimize COSS and if we can minimize RDS(on). Gallium nitride does this for us in a way that allows us to make more efficient, cooler running, and more compact power supplies. Let me show you how. This is an axis. It's a little bit of a constructed axis, but I'm going to put physical size on the x-axis, and I'm going to put losses on the y-axis. Looking at RDS(on) and COSS for a standard MOSFET, you're going to have the losses with size are going to go down when they're related to RDS(on). So these are your RDS(on) losses. As a transistor gets bigger, the losses get smaller. However, as the transistor gets bigger, you have increased capacitance. So it turns out that the losses due to capacitance go up with size. So at some point these are capacitive related losses and these are resistive related losses. And the best you can do is at this point here where they cross. At that point, you have a minimum of capacitance and resistive losses combined. And of course, that's affected by the frequency at which you choose to switch. So the green here, let's imagine the green is a standard MOSFET. Now, gallium nitride is a very special substance, and that it's RDS(on), it's specific RDS(on), and that's the RDS(on) related to the size of the physical size of the device, is very low. And so that provides us with a far steeper decline of RDS(on) related to the physical size. And the marvelous thing about that is that the capacitance is also very low. So it still starts down here close to the origin, but it's a much shallower curve. So gallium nitride's losses occur at a minimum around about here. And you can use that to your advantage because there are things you can do with gallium nitride that are simply impossible with a MOSFET. So the benefits of the reduced losses when the combined COSS and RDS(on) losses is increased efficiency, reduced heat dissipation. And there's another benefit that comes out of this curve, and that is, if you remember, CV squared F has this F component, the loss is related to frequency. And that means that if you wish, you can increase the frequency that the GaN switches at, and that moves this crossover point, but it still gets nowhere near where the MOSFET is. And so you can increase switching frequency. Now, that's not always available to you because you tend to be limited to a certain extent by the magnetics and other parasitic elements in your circuit, but you're no longer limited by the speed of the switch. Okay, let's talk about increased efficiency due to GaN. I'm going to draw an axis here. This axis here is the load on the power supply, 100%. And I'm going to set that against the efficiency of the power supply. So up here we have 100%, but let's start at 80% because that's a good baseline for the kinds of power supplies we're talking about, and there's my 90% point. So a MOSFET-based power supply has an efficiency starting in the at light load in the low 80s. Let's take a 65 watt adapter flyback. Okay, and we're going to see it reaching something in the approaching 90%. So let's call it 90% efficient at full load. A gallium nitride based power supply, particularly one that's mounted inside an inner switch product that has a tuned switching mechanism, is going to start off higher in the light load, and in the full load, it's also going to be higher, as high as 93%. So what we're looking at here is a 3% improvement in efficiency, just due to the use of gallium nitride. Now, 3% doesn't seem like a lot. 3% is a relatively small number. But when you set it against where we are on the curve, what you'll notice is it's 3% of 10%, which are the losses for the power supply. So you're saving 30% of the losses that you would otherwise be generating in your power supply. That's 30% energy saved. That's 30% of the less energy you have to dissipate in your power supply. Less heat sinking, less size, longer lifetime, doesn't get so hot. So there are a variety of benefits. Now, the regulatory environment in which we operate tends to be much lower. And so typically you can meet the regulatory guidelines with a MOSFET-based power supply. But with a gallium nitride-based power supply, you can build something that's far smaller and more compact, lighter, easier to carry around, more power for the same size, however you want to think about it. And that's a market benefit. To learn more about Power Integration's exciting new technologies, go to power.com.